Today we're going to start a new chapter where we're going to practice using our vectors to solve what are called particle equilibrium problems. The steps to solving these problems are very straightforward. There are 3 steps. First, we are going to draw a free body diagram of the particle. What is a particle? For purposes in this class, we're talking about any kind of an object where all of the forces meet at the same location. So it could be a really tiny particle, like a little pin or a ring or something, or it could be a pretty large particle, like a crate. But if all the forces meet at the same location, we're going to be able to do this particle equilibrium analysis. We'll start by drawing a free body diagram. Our second step, once we've drawn that free body diagram, will be to write what are called equilibrium equations. These come from Newton's law of motion, saying that sum of the forces equals mass times acceleration, but we are assuming everything is in equilibrium, so acceleration is 0. So for two-dimensional particle equilibrium, that boils down to simply 2 equations. The sum of the x components of all of the forces will have to add up to 0, and the sum of the y components of all of the forces will have to add up to 0. Those are the only 2 equations available to us for a 2D particle equilibrium problem. When we have 2 equations, that means we can only solve for 2 unknowns. So our third step is to just solve for the unknowns. Now, because these problems are pretty basic, we like to make them a little more interesting with 2 special cases. So one thing you're going to see in the homework are some linear springs. Force in a linear spring is equal to a spring constant K times how much the spring has been stretched. So we'll say S is the change in length of the spring from an unstretched length. So when S is 0, it's unstretched, there's no force, and as S gets bigger in magnitude, you're going to have a larger spring force. So let's look at units here. S is going to have units of inches or meters. So K, the spring constant, is going to have units of newtons per meter or pounds per inch, or it could be pounds per foot. So when you multiply newtons per meter times meters, you get the force in the spring. The other thing that we toss in here that makes this chapter a little bit interesting are we will see a few pulley problems. And for this chapter, all we really need to know about pulleys is that the tension on both sides is going to be the same, and that is because we are assuming that we can neglect any friction. So tension is the same on both sides. So let's do a full example. This one has a spring in it. What's going on here is we've got a spring and a rope AB, and a spring that goes from A to C. And somebody is taking point A where they connect with each other and pulling straight down. So it's particle equilibrium because the force in this rope, the force in this rope, and the force on this spring, they all meet at point A. So we're going to draw a free body diagram of point A. And what the problem tells us is we're applying a force P of 80 pounds. When we do so, the spring is going to stretch out. We're supposed to actually figure out how long it was before it got stretched out, but in its stretched out position, we're told that the angle theta is 60 degrees. They tell us how long this cord is, 2 feet long, and they tell us the spring constant, 50 pounds per foot. Before you jump in trying to use information about that spring, follow my recipe. The recipe says first draw a free body diagram, then write equilibrium equations, and finally solve. So we're only going to bring in information about our special cases when we need them, usually in the solving process. So free body diagram of A. Point A, it's just a dot. Pulling straight down on the dot is P of 80 pounds. Just write down the 80 pounds since we already know it. And we're going to have a force in AB. That's the force in the rope. We'll just call it the force in AB. All a rope can do is apply a tension force. So what that means is if I cut this rope, the 2 halves of the rope are tugging and pulling on each other. So when I draw a free body diagram, the rope is pulling up that direction. The spring will also be pulling up that direction. I've got the force in AB drawn on there, and I will also have a force in the spring. You can call it the force in AC. This looks like something I can solve. The free body diagram has 3 forces on it. Only 2 of them are unknown. I'll be able to write 2 equilibrium equations, which means I can solve for those 2 unknowns. But to write the equilibrium equations, I'm going to need to break AC and AB up into their x and y components. To do that, I'd really like to know their orientations. Well, AB is along this right here, and we've been told that theta is 60 degrees. If you guys remember alternate interior angles, if I draw an x-axis there, if that is 60, this is also 60 degrees. And if you like, you can write those angles on your free body diagram. You don't have to though. I feel like as long as you have another diagram somewhere where it's clear what that orientation is, that's perfectly fine. Now we need to figure out the orientation of that spring, AC. There are a couple of ways to do it. So what we know is we have a triangle where we know one side is 4 feet long. This rope we're told is 2 feet long, and that angle is 60 degrees. You can use law of cosines on this. We know a side, we know an angle, and we know another side. This turns out it's actually a 30, 60, 90 triangle, and this one is a right angle. I had to actually do law of cosines to figure this out, and then I felt really silly for not seeing it before. When you have a 60-degree angle and you've got one side of the triangle that's exactly half the other, do you remember in a 30, 60, 90 triangle, the side opposite the 30-degree angle is half the hypotenuse. To get this, I actually needed to use law of cosines. Shall we write it down? Law of cosines said that side AC squared is equal to A squared plus B squared. So the other two sides are 2 and 4 minus 2 times the two sides I know, 2 times 4 times the cosine of the angle between them. So we solve for AC. Length of AC comes out to be 3.464 feet. Now we need to use law of sines to find, say, this angle over here. So remember law of sines, we're going to use a sine of angle divided by a side, sine of angle divided by a side. So law of sines is going to look like this. Sine of 60 divided by 3.464 has got to equal sine of our unknown, call it angle C, divided by the side opposite it, which is 2 feet. Solving, you get that angle C is equal to 30 degrees. It is a 30, 60, 90 triangle. FAC then, if we again do alternate interior angles, if that angle up there is 30, this one is also 30. Okay, there's my free body diagram. I'm going to come back to this later in the semester when we do more complicated free body diagrams, but I do not want you drawing your forces on the original problem picture. I do want you drawing a completely separate sketch for every free body diagram in the whole semester. And there's a reason for that. The free in the word free body diagram means you have freed something from all of its external supports. It means in this case, we've cut this cable and we've cut that spring. And then we draw all the forces that act at A. So if you just start drawing forces on here with the rest of the supports still on there, it's incorrect. You always have to draw a separate diagram with the supports removed, the cables cut. So step 1 for the free body diagram. Step 2 is what I call the equilibrium equations. They look like this. I'm going to add up all the x components of the force and they have to equal 0. I like to choose a sign convention such as right being positive. So what I'll end up with is FAC times the cosine of 30 will give me the x component of this. This FAC, to get the x component, I'm using a triangle, and the x component is adjacent to 30, and adjacent always goes with cosine. That acts to the right, so I put it in with a positive sign. Now, the x component of FAB acts to the left, so it's got to have a negative sign, FAB, and this one will be cosine of 60 degrees equals 0. There's one of my equations. Next, I can sum forces in the y direction. If I do that, acting upward, I've got the vertical component, FAC sine of 30, and the vertical component of FAB also points upward, so it also gets a plus sign. Finally, minus 80 pounds equals 0. And we need to solve those simultaneously. My approach is to start with the easier of the two equations and get one of the variables all by itself. I will end up with getting that FAC is equal to FAB cosine 60 divided by cosine 30. That's 0.57735 FAB. Now I'm going to take that and I'm going to plug it in for FAC right here and solve. I end up getting, I've got 0.57735 FAB times the sine of 30 plus FAB times the sine of 60. Let's bring the 80 pounds to the other side. So we have plus FAB comes out to be 69.28 pounds. We can just plug that back into, I guess it was the purple equation, and get FAC. And doing that, we get that FAC from the purple equation is 40 pounds. Okay, my calculator gave me 39.999998. I'm going to round that to 40 pounds. If you want to write 40.0 pounds to really drive home that you did do 3 sig figs, that's a great option too. That was a solving step. So right here, we are solving. We solve for FAC. We're not quite done. FAC is the spring force. The problem asks for the unstretched length. Remember our spring equation? Spring equation said that the force in the spring is equal to Ks. We know the force in the spring, 40 pounds. We were given K, 50 pounds per foot, and we can solve for S. Solving, we get S equals 0.8 feet are the units. And do you remember what S is? S is, for a spring, the change in length. So we know the spring is currently 3.464 feet, and it changed in length by 0.8 feet when somebody applied this big tension force to it. So the unstretched length will be the current length minus the length change, which is our 3.464 feet minus 0.8 feet. So the answer to the question is 2.66 if we round to 3 sig figs. So that's how long the spring would have been before we applied any force to it. Let's do another example. This one has a pulley. Remember, a pulley means that the tensions on each side have to be the same. The rope is a continuous rope, goes around a frictionless pulley. It's going to pull the same force on each side. We've got another rope that's supporting it, and we have a crate being held. And what we're told is that both of these cables can both only support a maximum load of 100 pounds. So what is the maximum weight of the crate and the angle for it to be in equilibrium? And I think you guys can probably see that if the crate weighs 100 pounds, you would have exactly 100 pounds of force in this cable, and that cable would be right at its limit. So you're not going to be able to carry a crate that weighs more than 100 pounds. The question really becomes, what is the force that's going to cause cable BD to fail? But let's do our tried and true formula. We're going to start with a free body diagram of a particle. We could draw a free body diagram of the crate itself. Let's do that. Free body diagram of the crate. The crate is acted upon by the tension in cable ABC. It's a single cable, so it's got a single tension. So let's just label it with all 3 of the letters. Acting downward would be the weight of the crate. Summing forces in the y direction, we get that the weight in the crate is equal to the tension in ABC. The more important free body diagram here, though, is the free body diagram of pulley B. And we're going to treat that pulley like it is a particle, because all the forces meet at that pulley. We're not given a radius of the pulley, but it turns out it doesn't matter. It can be a big pulley or a really small pulley. All the forces meet at one location. So let's draw that free body diagram. And what I have is a tension in cable BD. And then in order to draw this, I had to cut, right? Here's a hint for pulleys. Anytime you cut a cable, you need to draw that tension on your diagram. If you don't cut a cable, don't draw the tension on the diagram. Cutting the cable, downward, I've got the tension in, we'll call it ABC. And over here in this direction, I got the tension in cable ABC as well. That's the whole free body diagram. If you want to draw angles on here, you can. This is that unknown angle theta. And this one, we're not given an angle, we're given a similar triangle. We're told that it has a slope of rise 12, run 5. And the way we draw that is it's a 5, 12, 13 triangle. Gives you the slope. Okay, that was step 1. Draw that free body diagram. Step 2 is write our equilibrium equations. We need to sum the forces in either the x or y direction. I almost always do x first. They have to add to 0. And I always write down my sign convention to remind myself that anything pointing to the right is positive, left is negative. So this tension right here is in the y direction. So there is no x component. It doesn't need to be in this equation, but this one does. And we're going to practice that shortcut I told you. If I want to get the vertical side, I'd use the 12. If I want to use the horizontal side, I'd use the 5. And then I have to divide by the hypotenuse to turn the side into basically a sine or cosine. So what I'm doing is in the x direction, I'm going to have TABC. The horizontal side is 5 and the hypotenuse is 13. So that 5/13 takes the place of a sine of theta or cosine of theta. It is the sine of an angle or the cosine of an angle. The other thing I've got acting in the x direction is to the left, I've got a TBD times cosine of theta equals 0. Let's write the summation of force in the y. That also has to be 0. So upward, I've got TBD sine theta. How did I figure out which one was sine and which one was cosine? The side adjacent to theta gets cosine, and the side that's opposite theta gets the sine. Then downward, I've got a single TABC, and then I've got a component of TABC. This one I'm going to use the 12 because the 12 is the vertical side, again, over the hypotenuse times TABC equals 0. We had a little bit of a problem here. I count 3 unknowns in those 2 equations. And part of why there's 3 unknowns there is that I haven't yet put in my information that I'm going to set one of my cables equal to 100 pounds. But it turns out if we simplify these 2 equations, we can actually solve for, because it turns out that the angle theta for this to be in equilibrium does not depend on how big the crate weight is. So there's a little bit of a mathematical trick that helps us solve this problem a little faster. Let me rearrange these 2 equations. I'll end up with TABC times 5/13 on the left, and on the right, I'm going to write TBD cosine theta. So just bringing the TBD cosine theta to the right. And then what I'm going to do for the second one is I'm going to group these 2 TABCs and bring them to the other side of the equation so they're positive, but I'm going to write it directly under this other TABC. So on one side of the equation, I've got TABC times, I've got 12/13, and I've got 1, which I can write as 13/13. So if I combine them, I get 25/13 on one side of the equation. On the other side of the equation, I've got TBD sine theta. If I were to take these 2 equations and divide them by each other, right? Basically, I'm going to divide both sides of this equation by the same thing. Only the way I do that is I say on this side, I'm going to divide it by this, and on this side, I'm going to divide it by that. And since they're equal to each other, I'm dividing the equation by the same thing. This is allowed as long as the thing you're dividing by is not equal to 0. And in fact, I'm going to reverse the order of these. I'm going to take this equation and I'm going to divide it by this and this. So dividing, let me write it out in steps so I don't lose anybody. TABC times 25/13. We start with our equation, TBD sine theta. And then I'm going to divide by TABC times 5/13. I'm totally allowed to do that as long as TABC is not 0. And on the right side, I'm going to divide by what that's equal to. So I'm dividing by the same thing, TBD cos theta. Now this is cool. What happens? The TABCs cancel, the TBDs cancel, and even the 1/13s cancel. So what I get is 25 divided by 5 is 5. Sine over cosine is tangent of theta. Theta is 78.7 degrees. The cosine of theta is not 0, and this division was legal. So we solved for the first part, which is what is the angle that you have to have here for this setup to be in equilibrium. Now, what we're going to do is solve for the weight of the crate so that neither of the cables fails. We already know that if the crate reaches 100 pounds, ABC is going to break. So what I want to look for is what is the weight of crate that would cause BD just on the verge of breaking. So let me write all that down. If the weight of the crate equals 100 pounds, TABC equals 100 pounds. So this is a possible solution where rope ABC is the limiting factor. But what I want to check is we have an equation that relates TABC and TBD. We actually have 2 of them. I can use either my X force equation or my Y force equation or the simplified versions of them. Let's plug in that TABC with that theta and solve for TBD. So if TABC is 100 pounds, one of my equations says TBD cosine theta equals 5/13 TABC. Plugging in the 100 pounds and the 78.7 degrees, that gives me TBD would be 196 pounds. So this would fail. So that is not the answer. Instead, what we want to do is set TBD equal to its max value, 100 pounds, and let's solve. So using that exact same equation, we'd have 100 pounds times the cosine of 78.7 degrees, with more decimals in your calculator, is equal to 5/13 TABC, Or we can actually replace TABC with the weight of the crate if we want. And solving, we get that TABC, or the weight of the crate, is 51.0 pounds. And that's actually the biggest crate that you can hold with this group of cables, because that is right at the limit where cable BD is right about to fail. Cable ABC can totally handle more weight, but cable BD can't. So there's your answer. Okay, let's talk 3D equilibrium of particles to finish out class today. We just did particle equilibrium in 2D. If we wanted to move up to 3D, well, we're going to need equilibrium equations again, and we'll use a free body diagram as well. But now our equilibrium equations are going to be sum of forces in the X still have to be 0. Summation of all the Y component forces still have to be 0. But now summation of forces of the Z component also have to be 0. So we now have 3 equations. So we can solve for up to 3 unknowns. So let's practice this with an example. So what I have here is a crate. We're told it has a weight of 300 pounds. It's sitting right down here. And we're supposed to find the force in these 3 supporting cables. Cable AB is aligned with the x-axis. Cable AD, we're given the direction angles. And cable AC is a spherical coordinate situation where I have those 2 angles. Looks like a lot of work. I think we are up to the task. Step 1 is always draw a free body diagram. What are we drawing the free body diagram of? I'm going to draw a diagram of point A. So free body diagram of A, because that's where all the forces meet. I'm going to have a downward force in this little rope that is equal to the weight of the crate. We can draw a free body diagram of the crate if we want, but I think we can skip that step. So let's just draw point A. That's the interesting point. Acting downward is the tension in the rope, which is equal to the weight of the crate, 300 pounds straight down. Then I have the tension in AB off in that direction, tension in AC off in that direction, and the tension in AD. And here's an example where I don't even want to try to draw all the angles on there. It'll just be a messy diagram. The point of the diagram is to recognize which way is the force pulling. Is it out and away or pushing in toward the point? And how many forces are there? So that when we write our equilibrium equations, we don't miss any. Our second step will be equilibrium equations, but I'm going to do kind of maybe a 1B step, which I usually need to do for 3D problems. With 3D problems, I really need to write down all of these vectors in their Cartesian components, because some of these are really complicated and this is a lot of work. And I just like to be able to, when I'm done, go and grab all the X components and add them up. Grab all the Y components and grab all the Z components. Let's start with AD. What we're doing first is getting all of our vector components for every force. So the tension in AD, written as a vector, it has a magnitude that I don't know. So I'm just going to write it down in front as an unknown magnitude. And then inside of the brackets, I need to write its direction. If I have the angle to the positive coordinate axis, 120 degrees, I can just write this as cosine 120 degrees in the I direction. For the Y, I've got 60 degrees to the negative Y axis. So you can either write this down as minus cosine 60 or find the angle to the positive Y axis. If it's 60 to the negative Y, it'll be 120 to the positive Y. I prefer to write this as plus cosine of 120 degrees J, but you can write it as minus cosine of 60 if you'd prefer. And then finally for the Z, it's cosine of 45 degrees K. There is my force vector TAD written in its Cartesian components. Let's do AC next. It's got a magnitude that is unknown. I'm going to need to do the blue triangle method here. So to get the X component is going to be negative. And then to find the X component is going to be the side that's opposite the 30-degree angle. And then the hypotenuse is adjacent to the 60-degree angle. So what I'm going to have is cosine 60 times sine of 30. If you need to do the extra step and first break the tension in AC into a Z and a horizontal component, then use that horizontal component as your hypotenuse. That's where the cosine 60 comes from. Then use the sine of 30. So we're adjacent to 60 to get my hypotenuse, and then opposite 30. Adjacent means cosine, opposite means sine. Let's do the J component. J component, that's going to be positive, and it's adjacent to the 30 and also adjacent to the 60. So we'll use cosine 60 to get the hypotenuse, and then cosine 30 to get the side in the y direction. So we got cosine 60 in both of these. F cosine 60 is the hypotenuse. Then I multiply by sine to get the x and cosine to get the y. And then finally for the z component is going upward. And for the z, I only need one angle. I'm going to use a 60 degree and it's opposite the 60 degree. So I'm going to use plus sine 60k. And then the other two force vectors, we don't necessarily need to write them as force vectors, but I like to. Tension in AB. Well, it's got a magnitude and its direction is, it is pointed in the x direction. So for its direction, the unit vector is just I. You don't need like a length of this rope or anything else. It's simply pointed in the x direction. So the vector is TABI. For 300 pounds, call it the weight. It's going to be minus 300 pounds and the direction is K, or 300 pounds in the negative K direction. The ones that are in the X, Y, or Z direction are really fast and easy. So up next is equilibrium equations. We will have three of them. We can sum forces in the X direction. X is now pointed out at us, has to sum to 0. So now I'm going to grab all of the X components. So there's one here for TAD, there's one here for TAC, and there's one here for TAB. So I end up with TAD cosine 120 minus TAC cosine 60 sine 30 plus TAB equals 0. There is a very nice equation with three unknowns in it. I'm probably going to use that last. We can also sum forces in the y direction. Y is to the right, and just grabbing all these, I've got TAD cosine 120 plus TAC cosine 60 cosine 30 equals 0. And then finally in the z direction, that's upward. Got a component from TAD cosine 45, just grabbing all the k's. So I got a k here, k there, and a k there, plus TAC sine 60 minus 300 pounds equals 0. And I do want you putting everything on the left side of the equation with a 0 on the right side. I know this last equation, a lot of students would just want to say equals 300. It would get you the right answer if you do it right, but I have seen so many students drop a sign doing that. So put everything on the left with 0 on the right. This is three equations with exactly three unknowns. This can be solved. If we want to simplify this just a little bit, that first equation becomes, I got a single TAB and the TAD term that ends up being minus 0.5 TAD minus the TAC term ends up being 0.25 TAC equals 0. The second equation, we get a minus 0.5 TAD plus 0.433 TAC equals 0. And finally, 0.707 TAD plus 0.866 TAC equals 300. Now you can bring the 300 to the other side. So I'm not going to go through all the steps of solving this. I look for an equation like this that only has two unknowns and a 0. And I'll solve for one of them. Then I'll go to my next equation that only has two unknowns and I'll eliminate that variable from this equation so I can solve for example, TAC, plug it in and get TAD. And then I'm going to use this equation that has all three unknowns very last to solve for TAB. Solving all of that, we get TAB is 139 pounds. TAC comes out to be 203 pounds. And TAD comes out to be 176 pounds. Those are all rounded to 3 sig figs. Let's do a really quick concept question or two. Here is a nice 3D problem. My first concept question would be, what should be on the free body diagram? Assuming you're doing a free body diagram of the knot at A, where all of these ropes come together. Your answer should be the weight of the flower pot, the tension in AB, the tension in AC, and the tension in AD. You should have 4 things on there, every rope, because in order to draw that diagram, you have to cut through all of these ropes. So every time you cut a rope, you need to draw a tension. So we have 4 tensions, they all go on there. Next question, what will the X force equation be? When I ask this in class, this is multiple choice. And I'm asking students to figure out what should be in this equation. If you're looking in the X direction is coming out this way. Can you see that AB will not have any component in the X direction? The weight won't either. I'll only have a component from these 2 ropes. They'll each have a component. One is going in the positive X direction. The other is going in the negative X direction. So with that information, you'll be able to pull out the right answer. The right answer has a number times TAC minus a number times TAD equals 0. What is the number specifically? Well, you need to do a little bit of math, but we're just using this right triangle right there. It's got a side of 4, a side of 2. So you're going to use the side in the x direction. 2 goes on the top of the fraction, and the bottom is the hypotenuse. And since this is actually only a two-dimensional thing, the hypotenuse is 2 squared plus 4 squared. That's 20 square rooted. But to get this answer right in my multiple choice version, you didn't even need to get that number right. You simply had to recognize that you'll only have a component from these two ropes. They're the only two that have an x component, and they're in equal and opposite direction. Question number 3, what will the y-force equation look like? And the same idea, you didn't actually need to get the whole equation written out to figure this out. In the y direction, we're going to have a component of TAC, component of TAD, and a component of TAB, but no weight. And the C and D ones are both pointed in the positive y direction, and the AB one is pointed in the negative y direction. So with that much in mind, you're going to have something times TAC plus something times TAD minus something times TAB equals 0. That was enough to get the multiple choice version of the question right. Let me fill in what the actual number should be. For C and D, we already used the 2 side for the x direction. It's the 4 side of this triangle. See the 4 meters? So we're going to have a 4 on the top here, and then the hypotenuse is still square root of 20. And then in the opposite direction, we've got this triangle from A to B. It's also just a two-dimensional triangle. It's got a side of 3 and a side of 6. So in the y direction, we're going to have a 3 on the top of the fraction, and then I just need the hypotenuse of that triangle. So if I take 3 and square it, I get 9. I take 6 and square it, I get 36. You add those up and you get 45. So you would actually end up with a square root of 45 on the bottom. And finally, of course, which one are we missing? What will the z-force equation be? So looking in the z direction, now AC and AD don't have a z component. They're laying flat in the xy plane. So all we're going to have is the weight downward and then a component of FAB upward. So to get this right, you just had to recognize that. TAB times something minus the weight equals 0. That something is going to be the 6 over square root of 45. All right, a little bit of practice of kind of visualizing in 3D which tensions should have a component in each of your equilibrium equations.